Today we're discussing the chain rule as it applies to the trigonometric functions. Here we're asked to find the derivative of these trigonometric functions. In these examples, there's nothing new here. We just use the old rules for finding the derivatives of the trigonometric functions. But what about these functions? You see that no longer is our argument simply x. Here we've replaced the argument with 2x. Of course, here 5x squared minus 2x. Here 3 divided by x, and here the square root of x. So no longer is it just the sine of x, or just the cosine of x, or just the tangent of x. Finding the derivatives of these functions is a different issue altogether. To be successful here, or the only way to find the derivative here, is that we use the chain rule for trigonometric functions. It's not really the chain rule for trigonometric functions, but it's the chain rule applied to trigonometric functions. Generally, remember what the chain rule says. If v of x and u of x are differentiable, then the composition, that is v of u of x, is differentiable, and the derivative is as follows. That is, the derivative of v of u of x is the derivative of v evaluated at the original inside times the derivative of the function that's inside. So let's look at an example where, for instance, v of x is equal to the sine of x, and u of x is equal to 3x squared plus 5x. If you'll notice just a little bit of work here, that f of x, if we look at the composition v of u of x, that means we evaluate v at u of x. In other words, in place of x, we put 3x squared plus 5x. So our function f is really the composition of functions, v and u, and our function ends up being sine of 3x squared plus 5x. So the chain rule tells us how we can deal with that derivative. It says to find the derivative of this function is that we just evaluate v prime at u of x, and then we multiply with u prime. So as we look here, well, first we need to know what v prime is. And of course we know that v prime is simply cosine of x. Well, then we need to take v prime, which is cosine of x, and evaluate it at u of x. That is, put a u of x in the place of x, and of course u of x is 3x squared plus 5x. So v prime of u of x is simply cosine of 3x squared plus 5x. Now also, to find the derivative of f, we need to know the derivative of u. And of course that's very easy for us to do. The derivative of u is simply 6x plus 5. So now we have the components to calculate the derivative of f. So we simply put these together, and we see then the derivative of f is v prime evaluated at u of x, which we decided was cosine 3x squared plus 5x, there it is, times u prime of x, which is 6x plus 5. Now, as we've done before, what I really would like you to look at is compare this to what we have above. And think of the original sine function, the original function f of x, being equal to the sine of some expression which happens to be 3x squared plus 5x. Well, let's just say the sine of some expression. In other words, this is stuff about x. So when we find the derivative, here's what we did. We simply said, okay, the derivative of the sine function is the cosine function. That's what we got here. So it's a cosine of exactly what we started with, that is the cosine of u, and then we said times the derivative of the inside. See, the sine function was the outside function, 3x squared plus 5x is the inside function, so times the derivative of what's on the inside right here, u prime. And that ended up being, of course, the cosine of 3x squared plus 5x times the derivative of u, or u prime, which is 6x plus 5. And this is really the form that we'll use over and over again. that if we have a, well, let's just look at the next page. Basically a restatement of what was on the previous page, that the derivative of the sine of u, that is, u is some expression in x, is simply the cosine of u. I mean, the normal derivative of sine is cosine, so the derivative of sine of u is the cosine of u, but times u prime. That's where the chain rule portion comes in. Similarly, the derivative of the cosine function normally is negative sine. So the derivative of cosine of u with respect to x, assuming u is some expression in x, okay, so the derivative of cosine of u with respect to x is negative sine u, just like the regular derivative would be, but times u prime to satisfy the chain rule portion of what we're doing. And similarly, the other functions act in a very similar manner. The derivative of the tangent function normally is secant squared, but here we have the derivative of tangent of u with respect to x. So of course it's secant squared u times the derivative of the inside u prime. Likewise, derivative of cotangent of u normally is negative cosecant squared. Well, here, yes, it's negative cosecant squared of the same expression, but then times the derivative of the expression. And it follows for the secant function and the cosecant function. The derivative of the the secant of u, as you read, is the secant of u times the tangent of u, then times the derivative of u. And similarly, the derivative of cosecant, as you can see. And so we have the same relationship that we've had before. Of course, the new portion in each case is we follow everything with the derivative of the inside. Derivative of what we were originally taking the sine of, the tangent of, the secant of, or the cosine of, or the cotangent of, or the cosecant of. So following up with this product is the critical issue. Well, let's put this new information to use. Let's find the derivative of the function f of x is equal to cosine of 5x squared. Well, this is the cosine of something other than x, which means we're going to have to use the chain rule for the cosine function. So using the chain rule as it's stated here and it was previously, it's the opposite of the sine of the same expression times the derivative of the expression. So then the derivative of f is equal to the opposite of the sine of the same expression, which is 5x squared minus 2x, and then times the derivative of u, that is the derivative of the inside. So we're going to practice writing this. I understand that we could do this in our head, but let's write it so that we'll understand what we're going to be doing when it's more complicated. So the derivative of the inside. Well, of course, on the next line we can complete that derivative, so we'll have negative sine of 5x squared minus 2x times the derivative of 5x squared minus 2x, of course, is 10x minus 2. And I keep explaining to you that in the middle of a problem, when I'm completing a intermediate derivative, I always put those results in brackets so I'll be able to realize where they came from when I'm reviewing my work later. But now the brackets aren't needed any longer, so we'll replace them with parentheses. And it's normal to put this binomial in front of the sine function so that it looks a little neater. So we'll say the opposite of the expression 10x minus 2 times the sine of 5x squared minus 2x. And we'll look at another problem. In this example, we're to differentiate the function y equals secant of the square root of x. And because this is not just the secant of x, once again, we have to use the chain rule. So as we prepare to use the chain rule, let's see if we can remember. Oh yes, the derivative of the secant of some expression in x, that is, if these two do not match, okay, the derivative of secant of u is secant of u times tangent of u, then times the derivative of u. So we practice a great deal on writing this down. We're looking for dy dx. So dy dx is equal to the secant of the square root of x times the tangent of the square root of x and then times the derivative of u. And of course use the square root of x, so we need to write down times the derivative of the square root of x with respect to x. Now, of course, this is the only difficult part of our problem at this point. And so this is where we're going to spend a little bit of time trying to do some calculations. So let's see what we're going to do here. This is kind of over on the side of our paper. We're needing to calculate the derivative of, see, once we've written it down, we can kind of pause and figure out what we're to do. The derivative of the square root of x. Well, we've seen many times before that what we'll do is we'll write a square root as a power, and then we have the tools for finding derivatives. So rather than say square root of x, we'll say x to the power 1/2. Now that derivative is easy to calculate because we simply have 1/2, the exponent 1/2 as a coefficient, times x to a power that is 1 less than 1/2. Well, of course, 1/2 minus 1 is a negative 1/2. So we have 1/2 times x to the power negative 1/2. But we won't leave an exponent that is negative, so we recognize this as 1/2 times 1 over x to the power positive 1/2. And we may have been able to do this in one step, but now we recognize that that's nothing more than 1 over the square root of x. So we have 1/2 times 1 over the square root of x. And then, of course, we know how to write that. That would end up being 1 divided by 2 times the square root of x. So what we've done is we've calculated this portion of our derivative, and that was the reason it was important to be able to write this out so that we could come to the side and complete our work. So we'll go back now and we'll finish our work. The derivative, that is dy dx, is equal to, of course, the secant of the square root of x times the tangent of the square root of x, and then of course times this derivative, which we saw was 1 divided by 2 times the square root of x. Now we could actually write this factor in front, and normally we would write factors in front, but since this is a fraction, we could actually think about multiplying this out. We could, of course, understand or realize that this is a fraction over 1, this is a fraction over 1, and so we would end up having secant of the square root of x times the tangent of the square root of x in our numerator times 1, and then of course our denominator would simply be 2 times the square root of x. And that's probably the way we would prefer to leave our answer. And remember, as we've discussed before, when we're talking about leaving our answer for derivatives in calculus, it's rare that we rationalize a denominator if the radical includes variables as it does here. So this is the way we'd leave our answer. Okay, I'd like to look at a couple of examples before we go on to anything more serious. And really I want to compare these two functions and notice the differences and notice how we find the derivatives of each. And it has to do with the placement of the constant 2. Okay, in the first example, of course, we have y is equal to 2 times the sine of x. That is a constant times the sine of x. Of course, over here we have y is equal to the sine of 2x. And so this factor 2 is part of what we're taking the sine of as opposed to here. We know we can't move that 2 outside, so these are different functions. Now in the first example, we use the constant factor rule. And remember that from a while back, that when we have the derivative of a constant times a function, well, that's our 2 times our function sine x. Then to find that derivative, we simply say the constant times the derivative of the function. So in this case, when we're trying to find the derivative of y with respect to x, it will simply be the constant 2 times whatever the derivative of the sine of x is. Well, of course, in this case, the derivative of sine of x, this is a normal derivative of a tangent of a trig function. Our argument matches our variable here exactly, and so we remember then that the derivative of sine of x is simply cosine of x, and this final result would be 2 cosine x. Now, we have a different issue here because what we're taking the sine of is not simply x, and so we're going to have to use the chain rule as it applies to trig functions. And we saw before the derivative of the sine of u with respect to x is cosine of u times the derivative of the u. In this case, of course, the u is 2x. So as we look to find the derivative in this case, we say, okay, the derivative of y with respect to x is going to be, the way we'd think through this is normally the derivative of the sine function is the cosine function. But of course it's the cosine of the argument we have here, 2x. But don't forget that we have to multiply then with the derivative of the u, and the u is what's inside. And so we'll say the derivative of the 2x. And we recognize the derivative of 2x is easily 2, but I want us to practice writing down this step, the derivative of the inside. Okay, well, of course, the cosine of 2x we still have. We evaluate the derivative of the inside, that is the derivative of 2x, which of course is just 2, and then it will be very likely that we would write that 2 as a factor in front, so we'll say 2 times the cosine of 2x. And we notice that our results are similar but quite different also because we have a 2x here, but the approach was completely different between the two. Well, that sets us up to look at a more involved problem. So let's go and consider finding the derivative of this function g of x, which is 4 times cotangent of 3 over x. Well, we notice two things. We notice that we have a constant factor of 4, and we have an argument, that is what we're taking the cotangent of, is something other than x. It's 3 divided by x. So that means we're going to have to use the chain rule, and we're also going to have to use the constant factor rule. So we're preparing to find this derivative. We'll start by saying, okay, g prime of x is equal to. Now we've got to remember, well, let's just say it's equal to 4 times the derivative of the cotangent function. That is the cotangent of 3 divided by x. Well, here we have the derivative of a cotangent function. We've got our 4 here. Well, the derivative of the cotangent function, remember, is negative cosecant squared. Okay, so let's make sure, because we have a negative, I don't want it to look like a subtraction, so I'm going to put this in parentheses. It's negative cosecant squared of 3 over x, just as we've done before. But the extra part is that we have to multiply this with the derivative of the inside, the derivative of 3 over x. So we've got to remember how to do that little calculation. Before we actually do that, let's clean this up so that we see what we have. Well, 4 times this negative factor is going to be negative 4 times cosecant squared of 3 over x. And then we're going to concern ourselves with how we find this derivative. And that's not unusual. It's good that we've written it down in the way we have, so now we can concentrate on how we're going to actually find that derivative. Well, we've seen things of this nature before. Let's look at the derivative of 3 over x. First issue is the way it's written. If we could write this as a coefficient times the power of x, it would be something we could differentiate pretty easily. So we're going to write 3 over x as 3 times x to the power negative 1. And that sets us up to easily find the derivative. We'll say negative 1 times 3, of course, is negative 3. And then we'll decrease this power by 1, so negative 1 subtract 1 is actually negative 2. But then we'll never leave our result with a negative exponent, so we'll write this as negative 3 times 1 over x squared. And now we're in a position to recognize that that's nothing more than the negative of the fraction 3 over x squared. So we've found this derivative, and we'll put it in this position. I'll go ahead and just put it in here so that we recognize, oh, it's times a negative 3 over x squared. Well, now we see, after we've put these pieces together, we don't have a hard time keeping track of what we're doing because we've broken it into components. So we see we have a negative factor times a negative factor, which will be positive. So, and we also recognize we're going to think of this as a fraction, since we already have a fraction. So negative times negative is positive, and then we have a 4 times a 3 in our numerator, which will be 12. And we have cosecant squared x, or not of x, of course, 3 over x. So this composes our numerator, and our denominator is simply x squared. So here we see our final result, and of course it took a little work, but it wasn't too bad, since we had made sure when we wrote this out that we could come over and pause our machine, pause our thinking machine, and be able to do this calculation and then go back to the original problem. A very good lesson learned. Here's another couple of functions that I'd like to compare before we go on, and it has to do with exponents. And you notice in our first example, in our first function, we have y is equal to sine squared x. In our second function, we have, of course, y is equal to the sine of x squared. The simple placement of these two exponents makes a big difference on how we approach the problem. Now, we actually use the chain rule in both cases, but we use a different version of the chain rule, or the chain rule applied in a different way. Here we're taking the sine of something other than x, and so the chain rule applies to this being in the inside. But remember, when we have sine squared of x, that really means that we have y is equal to the sine of x, and that whole thing being squared. So what we really have in this case is the general power rule. We have parentheses or brackets with an exponent on the outside. And so that is the general power rule. So as we go about finding our derivative here, we'd say, okay, now that we've rewritten this in a form that we recognize we can deal with, the derivative of y with respect to x would bring down our exponent 2. We would decrease our exponent by 1. So we'd have the sine of x, of course, to the first power, and then we'd say times the derivative of the inside, the derivative of u. And so that would be the derivative of the sine of x. Well, we can simplify a little bit here, and we can actually calculate this derivative. Of course, we don't really need that exponent of 1, so we'll say this is 2 times the sine of x times the derivative of the sine of x, of course, is cosine of x. So as we finish, we have simply 2 sine x cosine x. And we're done with that portion of the problem. Now, that's again using the chain rule of a different style or of a different version than what we've been doing. But in our next example, we're going to use the chain rule as applies specifically. This is the general power rule, but as it applies to trigonometric functions. So here we're taking the sine of u, and so we'll say the derivative is the cosine function times the derivative of the inside. So we go back and begin to work on this then. The derivative of y with respect to x in this case will be, the derivative of the sine function is cosine function. But it's cosine, of course, of x squared. And then we have to say times always the derivative of the inside. Here the inside was sine of x, here the inside is x squared. So the derivative of the inside, the derivative of x squared in this case. And of course the derivative of x squared is nothing more than 2x, and so we'll have a 2x factor we'll write in front, and we'll have the cosine then, of course, of x squared. So our final answer here is 2x times the cosine of x squared. Once again, different functions, different approaches, of course different results. Well, that sets us up to do this last problem of this discussion. In this last problem, we see that we're again faced with a pair of things, that we have sine squared and we also have an argument that is other than x, and we're asked to find the derivative. So we begin our thinking here. We know that we're going to have to use a couple of ideas. Whoops. Let me get rid of, well, we can keep that red. But I guess the first thing I really want to realize is rewriting this function, because it's this exponent that I'm concerned about. So what we really have is the sine of 7x cubed, and that whole sign is taken to the second power. So we are going to use the general power rule once again, where the expression to the power is this sine expression. So to calculate the derivative using the general power rule, we'll bring our exponent 2 down, and we'll say then times the derivative, times the sine of 7x cubed to the power 1. So that was the general power rule, except the general power rule tells us we have to multiply with the derivative of what's inside. So now we've got to say the derivative of the sine of 7x cubed. So the derivative of an expression to a power is that power times the expression to one less power, and then times the derivative of the expression. Well, the way we've written this, we can kind of stop and think about pieces. Of course, this we can just rewrite as the sine of 7x cubed. So here we have 2 sine of 7x cubed. I apologize. Of 7x cubed. And now we have to figure out what this derivative is. I'm going to just making some highlights here. Well, this is the derivative of the sine function. Of course, to find the derivative of the sine function, if this is not simply x, then we've got to use the chain rule as it applies to the trig functions. So the derivative of the sine function is normally the cosine function. So we'd have the cosine of 7x cubed. But we also have to multiply with the derivative of the inside. Well, in this case, the inside 7x cubed. So now we've got to calculate the derivative of 7x cubed. You notice we're just cascading this so that each step is just a little bit more for us to deal with, but no big step involved. So now we see that we have, let's see, we still have 2 times the sine of 7x cubed times the cosine of 7x cubed, of course, times the derivative of 7x cubed, which is no problem for us to figure out. That is 21x squared. So now we kind of know we've done all the derivatives that are required of us. So now we can look to clean this up a little bit. We have a factor of 2 and we have a factor of 21x squared. And so we'll do that multiplication. And we'll finally write 42x squared. That comes from the 2 times 21x squared and times sine of 7x cubed and times cosine of 7x cubed. Well, I'm having difficulties today. I want to certainly be as neat as I can, and I'd like you to be as neat as you can as well. Times cosine of 7x cubed. So this problem actually had us use the chain rule 2 times in succession. And that may not be an unusual feature for things that we do in the future, an unusual feature for problems that we might do in the future. You can go back, you can replay this if you'd like to see how we did each step. Well, now we can apply these new techniques that we've learned in using the chain rules for trigonometric functions, where we have to use old techniques as well as new techniques. So here we're to find the slope of a tangent line to the function f of x equals sine of 3x plus 4x times cosine 5x at x equal pi. Well, of course, to find the to find the slope of the tangent line, we need to find the derivative, and then we'll evaluate the derivative at the value pi. So we begin by finding the derivative of the function f of x. Now, when we look at this function, we notice that it's actually the sum of 2 functions. So to find the derivative, we have to take the derivative of sine of 3x and then add to that the derivative of 4x cosine x. And I've emphasized here times, that is 4x times cosine 5x, because we're going to need to remember in a few moments that we'll actually have to use the product rule to find this derivative. Well, to find the derivative of sine x 3x, then we have to use the chain rule as it applies to trigonometric functions. So normally the derivative of the sine function is the cosine function, so it's cosine of 3x, just as it was here, but then times the derivative of the inside, the derivative of 3x. And so that's what I've written in this place. I haven't attacked here yet, because we recognize here we're going to have to use the product rule. So as we use the product rule on this piece, and by the way, I've gone ahead and determined that the derivative of 3x is just 3, so I've written this 3 in front of my cosine of 3x here. Now, to find the derivative of 4x times cosine 5x using the product rule, I remember its first function, that's 4x, times derivative of second function, well, that's the derivative of cosine 5x. And then it's plus second function, that's the cosine of 5x, times the derivative of the first function, and of course the first function was 4x. Well, from here we can pick it up and calculate some of these other pieces. Here at the beginning, of course, we have the 3 times cosine of 3x plus our 4x, and now we're looking at the derivative of cosine of 5x. Well, now to find the derivative of cosine of 5x requires the chain rule again. So we're going to have to say, okay, it's times what? Well, normally the derivative of the cosine function is negative sine. And so we have negative sine of the same argument, 5x. But then we have to multiply that with the derivative of the inside, the derivative of 5x. So the derivative of cosine of 5x is negative sine 5x times derivative of 5x. And then we have this plus sign. And of course, we have the cosine of 5x times the derivative of 4x. And of course, the derivative of 4x is simply 4. So here we have the cosine of 5x times the resulting derivative, which is just 4. Well, we can go back in and we can do some more work here. We see that we have 3 times cosine of 3x at the beginning. And now we notice that we have a positive 4x times some negative factors. And so we'll write, instead of plus a negative, we'll write minus 4x times the derivative, times the sine of 5x. And of course, the resulting derivative of 5x gives us simply 5. And then of course here we have the cosine of 5x times a 4, and we'll write the 4 factor in front so we won't be confused and think it's the cosine of 20x. So this is 4 times the cosine of 5x. Now, as we work through our problem here, we notice, of course, that we can do a little more simplification because we have 4x times sine 5x times 5, and we'll write that as a negative 20x, 4x times the 5. That is a 5. And so we see that we have 3 times the cosine of 3x minus 20x times the sine of 5x, and finally plus 4 times the cosine. Let's clean that up a little bit. Cosine of 5x. Now, this has been so long, we've kind of maybe lost track of what we're trying to do. We're actually trying to find the slope of the tangent line at x equal pi. And so now we'll evaluate, to find that slope, we'll evaluate this derivative at pi. So the slope will be 4 prime evaluated at pi. Make a little space here. So the slope we're looking for, the slope of the tangent line at x equal pi, is the derivative evaluated at pi, which simply means we're going to replace, of course, each x with a pi. So this becomes 3 times the cosine of 3 pi minus 20 times, now our x value is pi, so 20 pi times the sine of 5 pi plus 4 times the cosine of 3 pi. Before we go much further, we need to kind of decide how we're going to calculate the cosine of 3 pi, the sine of 5 pi, and the cosine of 3 pi. So I'm going to draw a representative unit circle. This is the way I remember. And so here's my unit circle. And of course this is 0. This is 1 pi. When we get to this position, when we go to here, we get to 2 pi. And of course back to here is 3 pi. So this position represents the distance of 3 pi around the unit circle. Now while we're at it, this would be 4 pi, and then back to here would also be 5 pi. So 5 pi and 3 pi leave us at the same position. And of course the coordinates of this point are -1, 0. So that means the sine or cosine of, the cosine of 3 pi is the value -1. The sine of 5 pi is the value 0. That's the second coordinate. And so now we're able to do a little more work. We have 3 times the cosine of 3 pi. Cosine of 3 pi is -1. Minus 20 pi times the sine of 5 pi, which is 0. And then minus 4 times the cosine of 3 pi, and of course the cosine of... And actually I just noticed, I apologize here, way up here, this is not 3 pi, it's 5 pi, isn't it? So that should be a 5 pi in this position. Okay, but regardless, the cosine of 5 pi is still -1. And of course this was a plus. I'm making mistakes all over the place here. So 3 times the cosine of 3 pi minus 20 pi times the sine of 5 pi plus 4 times the sine of 5 pi. And as we simplify, you see that we get a -3 minus a 0 minus a 4, or simply -7. So the slope in question is -7. Before we leave this discussion, I'd like to mention 2 common mistakes that students make that we need to be very careful of. So let's begin with the function. Let's say we're given f of x, let's suppose, is equal to the tangent of 3x squared plus 5. And we're asked to find the derivative. Well, the most common error that is made on a problem like this, and of course not all students make this, but we need to be very careful in the heat of a problem. Sometimes we get in a rush and we make mistakes. The problem is forgetting to leave off the derivative of the inside, that is the u prime. We recognize, I hope, that this requires the chain rule, and that's the big issue, is we first have to recognize that it requires the chain rule to find the derivative. And so a lot of times students will remember partially the chain rule. That is, we'll say, okay, finding this derivative, well, what's the derivative of the tangent function? It's secant squared, isn't it? So simply writing down secant squared of 3x squared plus 5 and stopping right there and doing nothing further. And of course this is incorrect. That's not the right thing to do. The correct thing to do is to remember that when we're taking the derivative of a trig function, okay, that we certainly, what we're taking, the argument of our trig function is not simply x, or the variable to the first power, then we do have to use the chain rule. So we remember the derivative of the tangent function, yes, it's secant squared, we remember that correctly, and it's secant squared of the same argument, so it will be 3x squared plus 5, but of course the critical part is, in the chain rule, is that we also have to multiply this with the derivative in the inside. And this is the part that is many times overlooked or in a hurry forgotten about. Okay, so this is the critical part. We cannot forget that. Important, important, important. And so in this result we would end up with, well, let's look at the derivative of 3x squared plus 5 is 6x, and so I'm going to go ahead and write that in front, 6x times secant squared of 3x plus 5. 3x squared, pardon me, plus 5. And so that would be our result. This is incorrect because we forgot to follow up with the product of the derivative of the inside. Now, a second common issue would be, let's take another example where we have maybe the function, let's say we're given the function, let's make it easy. Let's say g of x is equal to the sine of x cubed, it's x cubed, plus 5x squared. Okay, and we're asked to find the derivative. That is, find g prime of x. Well, of course, we recognize again this requires the chain rule. But sometimes the parts are mixed up. Sometimes students remember, well, okay, I'm going to find the derivative. I know I've got to think of the derivative of the sine function. I've got to have the derivative of the inside. Well, the derivative of the sine function is cosine, and the derivative of the inside, what is the derivative of the inside? Oh, let's see. The derivative of x cubed is 3x squared, and the derivative of 5x squared, of course, is 10x. Well, the components that we need are here, but we've done things in the wrong order. Okay, we've done things in the wrong order. That, remember, we don't replace the inside with the derivative, we multiply on the outside with the derivative. And so, once again, this is wrong. The correct way to do it, and we know the correct way to do it, is that we would say, okay, to find the derivative of the sine function, well, derivative of the sine function is the cosine function, but it's the cosine of exactly what we started with. I'm just not wanting to draw a curve for me here. So it's the cosine of x cubed plus 5x squared. So the inside remains the same. Once again, the inside remains the same. But what happens is we multiply on the outside with the derivative of the inside. So when we multiply on the outside with the derivative of the inside, of course, we know that we get multiplying with 3x squared plus 10x. So this would end up being a 3x squared factor, 3x squared plus a 10x factor, that's the derivative of the inside, times the cosine of the original inside, x cubed plus 5x squared. Now I have these are the two most common mistakes made. Be very careful. I have these summarized. Here we go, summarized on these next pages. This is the first mistake that's often made. Here's another example that that when we have the chain rule, we cannot forget that we have to multiply with the derivative of the insides. Many times students make the mistake and just do the general power rule without multiplying with the derivative of the inside, but we have to follow up with the derivative of the inside. And it's just the comments there, and you might read over that. You can pause and read over that. Or the second mistake that we many times see, that I many times see, and that is not uncommon at all, I wish it were, is that sometimes we replace the inside with its derivative. And that's what we just talked about a while ago. And for instance, if we had y is equal cosine of x squared plus 1, well, sometimes the mistake is made is to replace the inside with the derivative of the old inside. But of course, that's not right at all. We follow up, the inside stays the same, we follow up with a factor that is the derivative of the inside. Be careful, please.